Hi everyone, welcome to part 2 of lecture 6, and we will continue to continuous random variables. In this part, we will start with the expectation of continuous random variables. So remember that the expected value or expectation or mean is something the balance point of that distribution, right? And the mean of a continuous random variables is defined by the expected value of x, which is a continuous random variable, will be equal to integration of x times f of x, okay, from the negative infinity to the infinity. If you remember the previous classes, that you will see that is similar to discrete case, except that the PMF is replaced by the PDF, and the summation is replaced by the integration. Okay, so that is the only differences. So as in the discrete case, the expectation can be interpreted as the center of mass of a non-homogeneous rod, which is something like that, right? Let's say we have a physical system. I gave the same example in the discrete random variables, and we have some weights and at some points on that rod. Okay, so there will be some point here, and this point will be the center. Okay, and this system will be in balance, so there will not be any turning effect because of these weights. So actually, when we say the expectation, or when we say the mean of the random variables, actually we infer that kind of system. Okay, so also, again, as in the discrete case, the expectation is the anticipated the average value of x in a large number of independent repetition of the experiments. So let's say we have a range, and our expected value x can take any value between this range, right? Within this range. So in the first experiment, maybe it will get that point. In the second one, maybe that point. In the third one, maybe that point. So if I have repeat this process many times, so the average of all those values will be something in center. Okay, and that is the another definition of the mean. Also, the properties of the expectation in the discrete case are still valid for the continuous case. For example, the linearity. So if you remember that, the expected values also can be used in a function. Okay, I mean, if x is a continuous random variable with the given PDF f of x, any real valued function y, which is equal to g of x, is also a random variable. So we did the same thing for the discrete random variables. Okay, so that means the new random variable will be based on the function of x. And to calculate the expected value of y, which is the new random variable that is based on the function of x, you can figure out its distribution first. So what's that mean? For each x, you can use the given function, the function of x, and you can calculate the y values. And that means you also calculated the new PDF of that y. In complete analogy with the discrete case, this is not needed. Okay, so what I mean, instead of figuring out the y's and corresponding PDF, we can use the lotus, the law of the unconscious statisticians, and we can steal the expected value. So what I mean here, so let's say I have some random variable x, and which will take two values, 1 and 2, and based on g of x, I will calculate the y, right? And let's say that takes 2 and 3 based on that one. This one, as a result of some, or that give us a PDF, okay, and this will also give some PDF. Let's say the PDF star. These two x and y can be considered as two different random variables. That means they also have two different PDFs. And if I want to calculate the expected value of y, what can I do? The first option, I can simply calculate the y1 times the corresponding probability of that py1 times yn times probability of corresponding the corresponding probability, right? This is a one way. But instead, I can use the original random variable, which is x, okay? So that's mean, based on the lotus, the expected value of y actually is equal to expected value of g of x, okay? So that will be equal to g of x times f of x. What was the f of x? Which is the PDF of the x. So instead of using the PDF of y, we use the PDF of x, and we multiply this value with the function of x. And this term will be integrated between minus infinity to infinity. So this is equal to expected value of y. So if you remember from the discrete case, the expected value of a times x plus b was equal to a times expected value of x plus b. So this is still valid for the continuous case. Let me prove that one. So what is the expected value of a times x plus b, which is the integration of a times x plus b times corresponding PDF, right? So because this is a summation, I can expand this term, and I can write this term as a two different integration, or two different integral, which is the a times x times f of x plus b times f of x, right? Just I multiply this two term with this one, and I expand that integration. So this will return the a times, because this is constant and it can go outside the integral, and it will be a times integration of x times f of x plus, and same, the b is the constant, which is not depends on the x, which is the main variable that for that integration. So the b will go outside the integration, and it will be b times integration of f of x. So if you remember that term, this is the probabilities for each possible x, right? And what was the normalization axioms? The total probability will be 1, right? That's why this is the 1. And what is this one? This is the expected value of x, right? That is the expected value of x. So I can replace this term with expected value of x, and that will be 1, and I will end up with b. So this term will be a times expected value of x plus b. So as in the discrete case, we have still the same thing. The expected value of a times x plus b will be equal to a times expected value of x plus b. So that means I can take the coefficient of x, the random variables, and I can multiply that coefficient with the expected value of random variables, plus I can add the constant value. So, and another thing is, which is the first moment of the random variable. And I can also calculate the nth moment of the continuous random variable, okay? Which is the expected value of random variable x to the n. And I can calculate it as the expected value of x to n will be equal to integration of x to n times corresponding PDF, the PDF of the x, okay? So please keep those in mind. And let's look at the variance. First, remember the basic logic behind the variance. What is the variance? So let's say I have some points like that. This one, this one, this one, this one, this one, and this one. And let's say the average of these points is here, right? So the variance will give me the information about how these points vary from the mean, okay? So I can simply calculate that variation by looking at the distance between that point to the mean, right? These ones. For example, for this point, I have this distance. For this point, I have this distance. And also I can sum up them. What is this point? This is expected value of x, right? Because this is the mean of all possible points. This is the expected value of x. And these points, the random variables x, right? So what I'm gonna do, I will subtract the e of x from each x. However, for example, this point, this distance is positive, and this distance is negative. So in this case, these two terms can cancel each other. That's why, to avoid this kind of problem, I can take the square of that distance. So the variance will be equal to the expected value of x minus expected value of x squared. One can think that why we using the expected value outside of this parenthesis instead of using only this one, because this is related with the probability. So the x is not for sure, x is not constant, and it is not known in advance, or in other words, the value of x is associated with some probability. That's why we have to use the expected value. And that's why the whole term will be expected value of x minus expected value of x squared. And this will be equal to integration of this term, the x minus expected value of x squared times corresponding PDF. So please understand the logic behind this one. This is the distance square. This is the distance square, and this is the corresponding probability. Okay. As I said, because this distance is not for sure, it is not known in advance. That's why we have multiplying this distance with the probability. Okay. So this will be the variance. So it's clear that we have the variance of x will be greater than or equal to 0, because we are getting the square of that distance, and that is the same thing as we did in the discrete case. So let's look at the variance and how we can expand this integration. So which is the variance of x, as we said here, is equal to integration of x minus expected value of x squared times the PDF of x. So I can expand these ones, right? So what is this ones? This is x squared plus expected value of squares minus 2 times x times expected value of x, right? So that's mean I can rewrite this integral with with three different parts. I mean, I can multiply the PDF of x with this one first, this one, and the second I can multiply the PDF with this one, and the last one I can multiply this PDF with this one. Okay, so let's look at this one. First of all, this thing is the expected value of x squared, the x squared, right? The expected value of x was equal to x times f of x, right? The integral. So if this is squared, that's mean this term will be equal to expected value of x squared. So what is this one? This is the expected value of x. So this whole will be 2 times expected value of x squared. So I have one expected value of x squared here and minus 2 expected value of x squared. So one of them will be cancel each other, and I will have expected value of x squared. So the variance will be expected value of x squared minus the expected value of x squared. So this is the formulation of the variance, and it is same as the discrete case. So if you remember that from the discrete case, the variance of a times x plus b was equal to a squared times the variance of x, right? It is simply what I'm looking. I was looking at the coefficient of random variables, and I am taking the square of them, which is a squared, and I'm multiplying this term with the expected value of x and plus and nothing. So simply I will look at the coefficient of random variables, and I will get the square of them. That will be the a squared, and I will multiply it with the expected value of random variables. And this constant will not affect the variance. Okay, so and let's say let's do that for the continuous case. So we have just calculated the variance of the x, right, for the continuous random variable, which was the same as the discrete case. So what was the formulation of the variance of x? That was the expected value of x squared minus the expected value of x squared. So what is x here? Let's say which is a times x plus b. So I can just replace x with a times x plus b, and it will be the expected value of a times x plus b squared minus expected value of a times x plus b squared. So if I can open this part, right, and it will be the square of the first term, which will be the a squared times x squared, plus the square of last term, which will be b squared, and plus 2 times the first term times the second term, it will be 2 times a times b times x, and minus this one. And in this one, I can rewrite this part as a times expected value of x plus b, right? So as we did in here. So we prove that the expected value of a times x plus b will be equal to a times expected value of x plus b. So that's why I can rewrite this part as a times expected value of x plus b and the square of that. So also let's open this part as we did in here. So it will be a squared times expected value of x squared, okay, and plus the second term squared, which will be the b squared times say plus 2 times the first term times second term. Okay. So, and I will have this term. There will be some cancellation here. So let me do that. I have what I have here. These two b's, the b squares will be cancel each other, and this 2 times a times b times expected value of x, and I have minus same thing, so this will cancel each other, and I will end up with a squared times expected value of x squared, right? And minus a squared times expected value of x squared. So the common factor is a squared, so that will be a squared times expected value of x squared minus expected value of x squared. So what was this one? This one, the variance of x. Okay, we just did here. So I can simply write this part as a squared times variance of x. So again, as in the discrete case, the variance of a times x plus b will be equal to a squared times the variance of x in the continuous case. So simply, if I have something like that, I can look at the coefficient of random variables, and I can take the square of it and multiply that square term with the variance of random variables. That will give me the variance of that function, a times x plus b. Okay. So this is the end of part 2, and we will continue with the part